Hello, my name is John Wright, and today I'll be talking about the state hidden subgroup problem and an efficient algorithm for locating unentanglement. This is joint work with Adam Bouland and tutor Giurgica-Tiron. I'm going to begin this talk with a puzzle, fun little puzzle. So let's suppose that we have a state A on 4 qubits, and then another state, a pure state B on 4 qubits. And we put them together and we get a state on 8 qubits total. And note that since A is a pure state and B is a pure state, then if we draw this line separating the 4 qubits on each side, the overall state on 8 qubits has no entanglement across this cut. So what I'm going to do is I'm going to take these 8 qubits and I'm going to scramble them up. And I'm going to call the resulting state psi. And I'm going to define S to be the set of blue vertices. This is a subset of the numbers 1 through 8 of size 4. And then T is going to be the set of the remaining vertices, the purple vertices, also a subset of 1 through 8. And note that the state psi is unentangled across this ST cut. In other words, it's a product state across S and T. So now what I'm going to do is I'm going to take these 8 qubits and I'm going to remove their colors. So you no longer see which ones are the blue qubits and which ones are the purple qubits. And the hidden cut problem is the following. You're given copies of this n qubit state psi. In this case, n is 8. And your goal is to find S, the blue vertices, or equivalently to find T, the purple vertices. Okay, so this is a problem that you can actually solve simply using full state tomography. So how do you do that? Well, if you use full state tomography, you can just learn the entire description of the n qubit state psi. To do so, it's known that it's necessary and sufficient to use 2 to the n copies of the state. And once you have a full classical description of the state, you can just test every possible subset S until you find the one that psi is a product state across. So this definitely works, but unfortunately it requires exponentially many copies, so it is an inefficient algorithm. And the question that I'll be looking at in this talk is it possible to do this efficiently with poly n copies? So before I answer that question, what I'm going to do is begin by answering an easier question, which is suppose I had a guess for what S and T were. How do I actually tell if psi is a product state across S and T? And this is a problem, a simpler problem known as product testing. So let me define this problem formally and then show you the well-known algorithm that solves this. So in product testing, your input is going to be a bipartite quantum state psi AB on 2 registers A and B. And your goal is to do the following. You would like to output the word product if psi AB is indeed a product state across AB. So on the A register, it's cat A, and on the B register, it's cat B. And otherwise, you'd like to output that it's entangled if psi AB is epsilon far from product. And what that means is that the trace distance between psi and V is at least epsilon for every possible product state V. Okay, so it's at least distance epsilon from any product state. So let me write this pictorially. If this gray blob is the set of all states, the set of product states is going to occupy a very small region in this set. And then here in red is a set of all states which are epsilon far from product. Okay. And then we have this gray region. These are the states that are not product state, but they're also not epsilon far from product. They're within epsilon to product states. So these are not product states. They're not epsilon far from product either, but they're too close to product states to really tell one way or the other. Okay. So even though they're not product states, they're so close that it's going to be unfair to ask an algorithm to tell the difference. And so for states in this gray region, I'm just not going to care what the algorithm does. So this is just operating in the standard property testing model, product testing. Okay, and what is known about product testing? Well, the following fact is well known. There's an algorithm that solves it called the swap test. And the swap test has the following guarantees. So if psi AB is indeed a product state, then the swap test will always output the word product. On the other hand, if psi AB is epsilon far from product, then the swap test is going to output the word entangled with probability at least epsilon squared over 2. And furthermore, the swap test only uses 2 copies of psi AB at a time. And this means, if in the epsilon far from product case, I can detect it with probability at least epsilon squared, then all I have to do is repeat this test 1 over epsilon squared times, um, and I will detect it with constant probability, let's say 99% probability. And so that means I can solve product testing in 1 over epsilon squared copies. So how does this product test work? Oh, sorry, how does the swap test work? Um, so it's based off of a unitary matrix called the swap unitary. And given an integer d, the swap unitary is the following unitary. So it acts on 2 registers of d dimension each. And given 2 basis states, I tensor j, if I apply swap to them, it will output j tensor I. So it takes 2 states and it swaps them. So this is defined on the standard basis. But by linearity, this extends to an action on all product states. So for any U tensor V, if I apply swap to them, it will output V tensor U. So now let's try to build a test based off of this. So let's suppose that psi AB is indeed a product state. So we can write it as A tensor B. Now let's look at 2 copies of psi AB. So psi AB tensor psi A prime B prime. What I'm going to do is apply the swap unitary to the first register of each psi. So I'm going to apply it to A and A prime. Remember, psi AB is just, A tensor B. So we can expand both sides into A tensor B's. And then if we apply swap on A and A prime, what it's going to do is take the ket A and the ket A on the A prime register and swap these two. Um, but those are the same states. They're both ket A. So when I apply the swap to them, nothing happens to my overall state. And thus I'm left with psi AB tensor psi A prime B prime, exactly what I started with. So therefore, swap applied to the 2A registers. If I multiply this by psi tensor 2, it just gives me back psi tensor 2. Now, it's a fact, I'm not going to prove it here, but it is a fact that if psi AB is not a product state, but is actually epsilon far from product, then let's suppose we take psi AB tensor 2, and we apply this swap operator to it. And now we measure the overlap with the original psi AB tensor 2. So if it was a product state, this would be 1. But it turns out if you're epsilon far from product state, then this overlap, after you apply the swap operator, is actually bounded away from 1. In particular, it's at most 1 minus epsilon squared. Okay, so in summary, if psi is a product state, then if you apply swap to 2 copies of psi, you get back psi tensor 2. But on the other hand, if it is epsilon far from product, and you apply swap to 2 copies of psi, then the resulting thing has overlap at most 1 minus epsilon squared with the starting state psi tensor 2. So the swap test, what it's going to do is use 2 copies of psi to test. Is it the case if I take psi tensor 2 and apply swap to it, do I get back psi tensor 2 or not? And if psi is a product state, then the check always passes, and it always outputs the word product. And if psi is epsilon far from product, then the check will fail with probability at least epsilon squared over 2. And in that case, it will always output the word entangle. So that's the swap test. Um, Now let's move on to the more difficult problem of the hidden cut. So earlier we saw an informal definition of the hidden cut problem. Now I'd like to define it formally. So in the hidden cut problem, your input is an n-qubit quantum state psi, and it's promised to have a unique hidden cut s comma t. Okay, so pictorially, your state looks something like this. Some of the qubits are purple, some of them are blue. The purple ones are the t qubits, the blue ones are the s qubits, and you're a product state across s and t. Now, what does it mean to have a unique hidden cut? Well, there are two different ways that we can view this, and these are equivalent definitions. So it either means the following, which is that psi, it's a tensor product, A tensor B. But A and B themselves are both epsilon far from product states. Okay, so they're very non-product. Equivalently, we can just say that psi is epsilon far from product across any other S prime T prime cut, where S prime and T prime are just not equal to S and T. So we have a unique cut, and on any other cut, you're far from product. That's your input, and your output is supposed to be either S or T. Now, uh, our paper, I think, is the first one to actually introduce this problem, but a very related problem was first studied in this 2016 paper of Harold, Lin, and Montanaro. In particular, they studied the decision version of this problem. So what does that mean? That means you're given a quantum state psi, and you want to decide, does there exist a hidden cut, or is every cut epsilon far from product? And they gave an algorithm for this, which uses order n over epsilon squared copies, and it distinguishes the following two cases. So in the first case, there is indeed a hidden cut. Psi has a hidden cut S and T. And in the other case, they call it the case of genuine multipartite entanglement. And in this case, psi is just epsilon far from product across any ST cut. So their algorithm, it solved this decision version. It doesn't find the cut, but it tells you if one exists. More recently, there was this work of Montanaro and Jones from 2024 who showed a lower bound for the decision version of this problem. They showed that n over log n copies are necessary for this task. So they have nearly matching upper and lower bounds, at least in the regime where epsilon is constant. Now, their algorithm, although it is efficient in terms of the number of copies it uses, just polynomial, it is inefficient computationally. So it actually runs in exponential time. And I'll kind of describe their algorithm in a slide or two. Okay, so let me tell you actually an inefficient algorithm for not just the decision version of the hidden cut problem, but the search version. When you not only want to decide whether there's a hidden cut, but you actually want to find it. So we already saw earlier how to test if psi is a product state across a given cut S and T by using the swap test. So a natural thing to do is why not try this out for one cut S1 T1 and then for S2 T2 and then S3 T3 and so on until you finally find the right cut using the swap test. And that's exactly what we're going to do. So let me begin by talking about how do we just test for a single cut S and T. And then we'll look at how do you apply this for many cuts in sequence. So what we're going to do is we're going to take 2T copies of the state psi, like this, and we're going to group them up into pairs. Okay. And on every pair, I'm going to run a separate swap test. And we know that if S comma T is indeed the hidden cut, then every swap test is going to output the word product. But on the other hand, if S comma T is not the hidden cut, then every swap test is going to output the word product with probability bounded away from 1, at most 1 minus epsilon squared. So if I want to detect whether I am the product, I'm a product state across this cut, I just check if every test returns a word product, and if even a single one returns a word entangled, then I know I'm not a product state across this cut. So in this case where ST is not the hidden cut, then the probability that every swap test outputs the word product is going to be at most 1 minus epsilon squared to the t. And what we're going to do is set t to be order n over epsilon squared. Okay, so the same number of copies that Montanaro, Harrowlin, and Montanaro used for the decision version. Now, if I set t to be n over epsilon squared, you know, your overall probability is going to become 1 over 2 to the n. You know, like if t is 1 over epsilon squared, you have 1 over 1 minus epsilon squared to the 1 over epsilon squared. That becomes roughly 1 over e, and then we additionally raise it to the n power. That's how we get 1 over 2 to the n. So with this many copies, we can get exponentially small probability of outputting product in the case when we're actually entangled. Okay, so in other words, let me write pi s comma t to be the projector that corresponds to the case where I perform all the swap tests and they all return the word product. And I'm going to write pi st bar to be the identity minus this projector. So this is the case when at least one swap test returns the word entangled. And what this says is that if we look at the trace of pi st times, our 2t copies of psi, that's equal to 1 if st is indeed the hidden cut. And then it is at most 1 over 2 to the n if st is not the hidden cut. Okay, so now that was just for a single cut. Now let's see how we use this to actually find the hidden cut. So our input here, again, is going to be 2t, which is order n over epsilon squared copies of the n cubed state psi. And what we're going to do is the following. For every non-trivial cut, S and T, non-trivial means both S and T are non-empty. What we're going to do is measure our 2t copies of psi with this projective measurement that tests if S and T is the correct cut. And if we ever observe the first outcome, the pi st outcome, then we're going to output that S is the cut. And otherwise, we're just going to go to the next cut in the loop. Okay, so that's the algorithm. And let me give the proof of correctness. So each measurement, I claim it's going to error with probability at most 1 over 2 to the n. Okay, if you perform the measurement and S and T is the correct cut, then actually you will always get the right outcome. But if it's not the hidden cut, then you will get the wrong outcome with probability at most 1 over 2 to the n. So in both cases, you err with probability at most 1 over 2 to the n. Now, there are only 2 to the n total measurements you're performing. So just by a union bound, if we set the error probability, if we multiply this 2 to the n by order 1 over 2 to the n, we can make it so that the total error probability is at most some small constant, like 0.01. Now, you may say, but wait, hold on. Doesn't each measurement actually disturb the state? Can we use this kind of naive union-bound approach when analyzing this algorithm? And the answer is yes. You can. The analysis still works, even though the measurements, introduce disturbances using a quantum analog of the union bound known as Gauss quantum union bound. Okay, so everything works nicely. And this is basically the proof. All right, so this is very similar to Harrow, Lin, and Montanaro's algorithm for the decision version. It's not exactly the same, but it's similar. Um, We combine these, we have these 2 to the n different measurements, which test each of the possible cuts. We combine them using the quantum union bound. Harrow, Lin, and Montanaro, they took the same set of measurements and combined them instead using the quantum OR bound. Now, notice obviously this thing is going to run in exponential time because we're going over an exponential number of cuts. And so this is why it is an inefficient algorithm. Now, naively, this problem just seems to require exponential time, right? How else do you search over all exponentially many subsets? And this suggests the possibility of an information computation gap. Um, it's a problem where information theoretically it's solvable. We just saw an algorithm that solved it information theoretically, but there may be no algorithm that solves it computationally efficiently. And whenever you have information computation gaps, they're sometimes useful for example, in cryptography. And one potential application of this in cryptography is to the question of pseudorandom state length expansion. So let's say we took 2 pseudorandom states, ket A and ket B. One potential way that we could turn them in, take, 2 n-qubit pseudorandom states and generically turn them into a 2 n-qubit pseudorandom state is just to take the qubits, scramble them up, and then output ket psi. The question you might have is if A and B are pseudorandom, is psi itself also a pseudorandom state? And the answer is definitely no, if you can find the subset S, because a truly random state does not have any cut on which it is a product state. So, one of our results then is that actually we're able to break this candidate construction of pseudorandom length expansion, um, and show that this is not, a sound way of expanding pseudorandom states. I will say this is like, I think, a question a lot of people are interested in. How do you generically expand the length of pseudorandom states? Um, this is one where, as far as I know, there are like no known applications of expanding the length of pseudorandom states yet. But hopefully it's still an interesting question. Now, I personally like this question just because it's a very natural information theory question in quantum computing. I think it's just very, very clean, and yeah, I like it. Okay, so our main result, and this is a result that I'll be honest, I didn't think was going to be true. I personally find this surprising, is that there is indeed an efficient algorithm for the hidden cut problem, which uses n over epsilon squared copies and runs in time polynomial in n and 1 over epsilon squared. And one thing that's interesting about our problem is that the algorithm that we give is inspired by the hidden subgroup problem, which is, the classic generic problem that unifies Shor's algorithm and Simon's problem and, a variety of classic quantum algorithms. But ours is not like a classical problem. It's a state problem. You're given copies of a state and you want to determine something about it. And so, in the course of giving our algorithm, we have to define a quantum state analog of the hidden subgroup problem, which we call the state hidden subgroup problem. So, let me give you, yeah, the key idea of this, and how it relates to the hidden subgroup problem. Before I move on, I'd just like to mention that our algorithm is um, almost optimal, the number of copies that it uses, because of the Montanaro-Jones lower bound for the decision version. You remember they showed that n over log n copies are required for the decision version. We use n over epsilon squared. And my guess is that our upper bound is a tight one. Okay, so what does our algorithm look like? So let me tell you the key idea. Let's say we take 2 states, psi, And I'm going to write down a string x on top of the states. And the string x is going to have one bit for every pair of qubits. Maybe the first pair of qubits, we're going to have the bit 0, second pair of qubits, bit 1, and so on. And since psi has n qubits, the string x is going to be in 0, 1 to the n. So it's a length n binary string. Okay, given this x, I'm going to specify a swap operator, swap sub x, given as follows. So any pair of qubits where I have a 0, I'm just going to write the 2-qubit identity matrix. And any 2 qubits where I have a 1, I'm going to write down the 2-qubit swap matrix. Okay, so it's going to be tensor identity, tensor identity, tensor swap, tensor identity. And this is going to be a matrix that's in identity, comma, swap to the n. Okay, so you have n 2-qubit matrices. Each one is either identity or swap. Okay, so let me tell you some properties that these swap sub x matrices have. First, let's suppose s comma t is the hidden cut. Then let's say we take psi tensor 2 and we apply swap sub x to it. Then I claim that we actually get back psi tensor 2 for some nice strings x. So which x's does this work for? Well, first, when x is 0 to the n, then swap sub x is identity, and psi tensor 2 times identity is obviously psi tensor 2. But also, when x is the indicator vector for the set S, then what this does is it swaps all the qubits inside S and leaves all the qubits outside of S untouched. But we saw earlier, if I apply swap um, on one side of the cut but not on the other, it's going to preserve the state. Similarly, if I apply swap sub x, where x is the indicator of the t subset, then I'm just swapping the two parts of the state on the t qubits. And that won't change the state at all if it's product across S and T. And finally, swap sub x um, returns back psi tensor 2 on the string x, which is 1 sub s plus 1 sub t. Why is that? Well, s and t together form all of the qubits, so 1 sub s plus 1 sub t is just the all one string. In that case, swap is just taking the two psi's and swapping them. Okay, so yeah, 1 sub s plus 1 sub t is 1 to the n. And this is equivalent to just saying that swap, it leaves psi tensor 2 unchanged whenever x is inside the set H, where H is 0 to the n, 1 sub s, 1 sub t, and 1 to the n. And this H actually turns out to be a subgroup of Z2 to the n. Okay, so the binary strings of length n, with the group action being addition, this is a subgroup of that. Now, for any x outside of H, that x is going to be the indicator of some other cut, which does not correspond to the hidden cut. And so we already know that in that case, psi tensor 2 times swap x times psi tensor 2, that overlap is going to be at most 1 minus epsilon squared. One more thing, I think this is the last thing, is that these swap matrices, if I take swap of x and multiply it by swap of y, I get swap x plus y. So these swap matrices, they respect the group structure of Z2 to the n. And as a result, these swap X matrices actually form a representation of Z2 to the n, for those of you who are into representation theory. Okay, so what I want to say is actually this setup where we have these states and they wind up being invariant under these swap matrices so long as the string X comes from a subgroup. But otherwise, if we apply swap to psi tensor 2, it changes the state by some non-trivial amount. What I want to say is this actually looks like a classic problem from quantum algorithms, aka Simon's problem. So let me remind you what Simon's problem is. In Simon's problem, you're given oracle access to a function f, This function maps the n-bit strings into a set of, say, colors, red, green, blue, and so on. And this function has a property that hides a secret string s in 0, 1 to the n. What does it mean that it hides a secret string s? Well, if I take f of x and f of x plus s, so I take x and I shift it over by s, f is going to assign the same color to both of those points for every possible x. On the other hand, f of x and f of x plus z are never going to be equal to each other if z is a shift by any amount that isn't equal to s. Okay. So if I shift my function by s, it preserves the color. If I shift by anything else, it changes the color. That's what it means to hide the secret string s. And here your goal is to find the secret string s. Now, what I claim is that this is actually very similar to our hidden cut problem. So here we have an object, the Boolean function f. It is invariant when we shift it by an element of the hidden subgroup h, which contains either 0 to the n or the string s. And it gets completely changed when we shift it by any string z that is not in h. Okay? And our goal is to identify the subgroup h, which is equivalent to identifying the secret string s. This is similar to our hidden cut problem. In our hidden cut problem, we preserve the state psi tensor 2 if we multiply it by anything that's inside our hidden subgroup. And if we multiply it by something that's outside of the hidden subgroup, well, we don't completely change the state, but we do change it at least by 1 minus epsilon squared. Okay, so that's a problem. Now let me remind you, how do you solve Simon's problem? So this is, a classic algorithm. You begin by preparing the uniform superposition over all x and 0, 1 to the n. Then you query f in superposition. That gives you the state, ket x tensor ket f of x. And then you just Fourier transform the first register and you measure. And what that's going to give you is a uniformly random string y in h perp. And that y, it's going to give you a little bit of information about h, but it's not going to completely specify h. So you just have to repeat this process until h has been completely identified. So that's the algorithm for Simon's problem. And now it turns out, because of the similarity between Simon's problem and hidden cut, that we can actually write down a very similar algorithm for the hidden cut problem. Well, what does that look like? Okay, so we're given, copies of psi, and we want to find h, which is 0 to the n, 1 sub s, 1 sub t, 1 to the n. So what we're going to do is prepare the state, the uniform superposition over x, and then tensor psi tensor 2. And then what we're going to do is condition on the first register. We're going to apply swap sub x on the second register. And then we're going to Fourier transform the first register and measure. And it turns out, I don't have time to prove this, but this will always yield a string y, which is in the orthogonal complement of h. So that's in h perp. And then we just simply repeat this algorithm enough times until h has been identified. So that's the algorithm for the hidden cut problem, very similar to Simon's algorithm. Now, let me say one problem with this algorithm, which is unlike in the case of Simon's problem, the y that we get is probably not going to be a uniformly random element of h perp. Okay, it's has a potential to be very non-uniform. Why is this? Well, yeah, as we saw earlier, if x is not in the hidden subgroup h, then psi tensor 2 times swap times psi tensor 2, the overlap is at most 1 minus epsilon squared. And this is a non-zero number. It's actually very close to 1. So although, swap is going to change psi tensor 2, it may not change it by a lot. And so this is the annoyance that like y is not necessarily uniform. And the fact that it's not uniform means that you may need to take more and more samples to construct H. But it turns out we have a trick where you can actually amplify this overlap um, down to zero just by using more copies. And so trust me, everything works out fine, and we are able to get our n over epsilon squared number of copies. Okay, now Simon's problem, it's a special case of the hidden subgroup problem over Z2 to the n. But as probably many of us know, other hidden subgroup problems can be defined over more general groups G. And these hidden subgroup problems wind up having applications to a lot of, standard algorithms problems out there, like factoring, lattice-based crypto, graph isomorphism, and so on. And our hidden cut problem, it can be viewed as a state version of the hidden subgroup problem over Z2 to the n. And in the course of this paper, we also define a more general state hidden subgroup problem, which is defined over arbitrary groups G. And one of the results that we have shows that certain algorithms for the hidden subgroup problems over groups G will actually behave similarly for the state HSP over the same group G. So for example, our algorithm for the hidden cut problem, it can be viewed as us taking the standard algorithm for the hidden subgroup over Z to the n and using this correspondence to give an algorithm for the hidden subgroup for state hidden subgroups over Z to the n. Okay, so let me conclude with some final questions and open problems. Um, the hidden cut problem, I think it's a really fun information theory problem. Are there applications of it? So is it actually a problem that can be used anywhere? More generally, are there more applications of this of viewing of this hidden subgroup problem viewpoint to other state problems? And let me conclude with just one of my favorite open questions about entanglement. So as we saw, testing if a pure state is entangled is easy. This is something that you can do using the swap test. But it's still an open problem. How many copies do you actually need to test if a mixed state is entangled? So we have an upper bound for this problem. We have a lower bound for this problem. These two bounds don't match. And so it remains open to actually determine how many copies are needed to test mixed state entanglement. All right, that's the end of my talk. Thanks for listening.